Hello, class. It's Professor Rourke. So I had a few questions from 8.2 regarding a few different things. Chapter 8 can be tricky for a couple of reasons. One is there's some big ideas that can kind of just seem like, okay, I think I get it, but I'm not sure. The whole idea of a sampling distribution can kind of just be a lot to sort of wrap our heads around. So that's one problem, is just kind of the ideas. And then the other problem that can sometimes come up is like kind of the tedious nature of some of the formulas and being able to get that the correct number essentially. So let's go ahead and work through one. This technically is the first one we're going to look at is from the interactive assignment. It's like the fourth question that you're asked to do kind of towards the end. It says describe the sampling distribution of p hat. Assume the size of the population is 30,000. Okay, so first things first, whenever they say sampling distribution, you need to think like, oh, okay, this is the more complicated version. This is not a sample. This is not a population. This is talking about like repeated samples of size, whatever they're telling us. So they're telling us we're taking repeated samples of size 600, and we know that the population proportion should be 0.206. So chapter 8 is really the connecting piece to kind of take us from what we're going to do, how we can analyze information about population, to taking a sample and then trying to do the reverse and make inferences about the population. So 8's kind of the connective tissue that can sometimes feel a little jumbled. So first things first, it says describe the shape of the sampling distribution, and we have to say whether really there's like two things going on here. One, they're like, is it approximately normal or not normal? Spoiler alert, they're all going to be approximately normal for these answers, because otherwise we're not going to be able to continue on, right? Everything we do is based off of chapter 7. It's all based off of the normal curve. So we need the options that are saying it's approximately normal and why is it approximately normal, and then they talk about these conditions. So the sample size needs to be less than 5% of the population, and n times p times 1 minus p needs to be greater than or equal to 10. Okay, and it can be tricky because they have these, like they look exactly the same, but just kind of the reversed symbols. Just a couple notes about that. The rule of 10 is what we call the n times p times 1 minus p is greater than or equal to 10. This is the rule of 10. And if you look on your formula sheet, that's on there as well, because sometimes people can just kind of get confused about that. Believe it or not, they mentioned this back in chapter 6. Because proportions are sort of combining together what we did with binomials, right? Where like there's like probability of success and probability of failure. And then we were like, oh, how can we make this look normal? And we talked about how you can increase the sample size. And some real smart person was like, oh, let's just call it the rule of 10, because that's a good way to do it. And I'm like, okay. And then the other one, again, is that the sample size, other condition they talk about here, little n has to be less than or equal to 5% of the population. You're like, why would you want the sample size to be small? But we don't want the sample to be so big that we're sampling the same people over and over and over again, right? So we want a big sample, but we also need it like to be like relative to the population. We can't, if this population's only 100 and our sample size is 50, like we're not going to be able to get a lot of random samples from that. That we're going to be sampling the same people. So we need the sample size to be less than 5% of the population. Okay. Next up, determine the mean of the sampling distribution. So again, whenever I feel like if you see sampling distribution, especially like on a test or something towards the end, just sort of, this is a section I would really rely heavily on that formula sheet that I'm going to be giving you, because I know it can just be very complicated with the different types of formulas and symbols. So I have on here for you, like the mean is of the sampling distribution of the population proportion. Even just like saying that out loud sounds crazy, but the mean of the sampling distribution of the sample proportion is just p, the proportion, the population proportion. Okay, so that would just be 0.206. We don't have to do anything for that. The last piece here, the standard deviation, that's the one where it can sometimes get a little bit jumbled up because it's a little yucky. It's kind of a complicated like order of operations type thing that you might have not had to worry about for a little while. Okay, so again, you either you have it memorized or you have the handy dandy formula sheet. The standard deviation of the sampling distribution of the population proportion, again, just like saying it out loud, sounds ridiculous. Is p times 1 minus p all divided by n. That's a strange looking p there, but that's okay. And then you're gonna take the square root of all that. So it's quite complicated. So you do have the option to put this in your graphing calculator all in like one step, if you feel comfortable with your graphing calculator. If you are not comfortable with the graphing calculator, which I think is kind of who I had most questions from, or not, everyone's different. I'm going to show you how to do that as well. Okay, so for this particular problem, P is 0.206, right? So just to kind of write this all out, if you did want to put this into your calculator all at one time, this is how I would recommend you do it. You have the square root symbol, and then you have one extra large, doesn't look large on your graphing calculator, but a parenthesis to start out the square root, what you're putting inside the square root, and then another parenthesis, 0.206, close parentheses, new parentheses, 1 minus 0.206, close parentheses, divided by 500, no, sorry, 600. The last one I did, I think, was 500, sorry, divided by n, which is 600. And then we're going to close off that parenthesis, and yet that will give you the correct standard deviation if you want to try the graphing calculator. But if you are like many of us who maybe like haven't used the graphing calculator a lot, or just prefer to have the option to kind of use your phone calculator, or even just the kind of basic calculator that comes on with the computer, I'm going to show you how you can do that. Okay, so first things first, the problem that most of where we kind of start with is that we have to subtract 1 minus 0.206 first before we begin anything else. Okay, so first things first, we'll go to our calculator and we'll just do 1 minus 0.206, and that gives us 0.794. So I think most of the time it's kind of time consuming, but if you write down like the numbers along the way, that sometimes can help with some of the issues. So I'm going to go ahead and write down that one. I'm going to replace 1 minus 0.206 with 0.794. And then from here, we can go ahead and put in everything inside that square root in one step. Okay, so what I'll go ahead and do is I'll say, it's like, because order of operations like multiplication and division could be done at the same time. It's the subtraction piece that needs to be done first, either way. So I'm going to go 0.206 times 0.794, and then I'm also going to go ahead and just click divided by 600. Okay, and that's going to give me this gross number. It's fine. It says 2.72 e negative 4. For those of you who have taken like any sort of chemistry class lately, that's like scientific notation. That's how the calculator shows, like this is times 10 to the negative 4. It's just saying it's a really small number, but we need to take the square root of that. And so on your phone calculator, like if you rotate your phone, you'll find the square root symbol there, but also on this just like on the Windows calculator that I'm using right now, you can just hit the square root symbol and it will give me the correct standard deviation, which is 0.01. This one is 6, but it's around to 3 decimal places, so the 5 would bump that to be a 7. Okay, so I'd say 0.017 for that standard deviation. Okay, so that I feel like is one particular issue when solving some of these problems in 8.2, really just kind of being able to calculate the standard deviation correctly. Even if we have the formula, it can be quite tricky. Okay, we're going to take a look at another one that is sort of similar but different. Okay, another problem that can be problematic for our class often is the problem that is like question number 4 on the homework. Okay, so just to kind of give a little background, this is like a smaller skill that is required for some of the more complicated problems. What we're going to do in this next one. So there's a few problems just kind of sprinkled into the homework that might ask you to do this, and it might look different than some of the other problems because it's just kind of like, oh, let's go off on the side and talk about how you would do this. And so the main idea is that um, really essentially like the sample proportion. Whenever we talk about proportion, right, we're talking about taking, let's say talking about the proportion of people, I don't know, who have their ears pierced. So we'll take the number of people who have their ears pierced, whatever we're talking about, whatever we're looking for the success, and we divide by the total sample size, right? So in the last problem that we saw, they told us the population proportion. They didn't give us any context, but they were like, oh, hey, just so you know, P is 0.728, and N was I don't know. I think I forget. No, it was like 600 or something. Okay. Occasionally, especially when we start using StatCrunch in the next chapter, they're going to want us to find the number of successes. Okay, so they're essentially like there's always three pieces of information that that we can determine, and they usually give us two of them. Okay, so either they give us the sample proportion and the sample size, or they could give us the number of successes in the sample size and we could figure out the sample proportion, right? We could kind of find any of these pieces. So that might be overly complicated way of just saying, let's look at this problem. It says in a poll of 567 human resource professionals, 39.9% said that body piercings and tattoos were big grooming red flags, which we're just going to ignore. We're going to ignore what this is even talking about. I don't know. Just we're going to let that go, but it's fine. We're not going to think about that. We're just going to focus on the fact that they're saying in a sample size of 567 people, 39.9% said that body piercings and tattoos were big grooming red flags. Whatever. Okay. So they're telling us the sample size, right? They're telling us N is 567. And they told us the sample proportion as well is 39.9%. Now, I'm also going to go ahead, I recommend you do this as well. I'm going to write this as a decimal. I feel like it's always confusing, like, do they want it as a decimal, do they want it as a percent? But mostly, we're just going to be using percent decimals because even though percents, I feel like are easier to kind of understand in context, decimals are what we need to do performing calculations. So we just kind of go back and forth a lot. But they tell us again that N is 567. The sample portion is 39.9%, which is 0.399. But it's like, okay, so how many of them actually said yes, right? Like if they asked 567 people, do you think body piercings are a flag, a red flag or something? How many of them said yes, essentially? So really, we're just finding 39.9% of 567. That's all we're really doing, right? In terms of this like formula piece here, right? They're telling us that the sample proportion is 0.399. We don't know what X is, but we know the sample size is 567. So how are we going to solve for X? We're just going to multiply, right? We're going to multiply 567 times 0.399. So you can think about it that way. You can think about like the formula way, or if you don't like that, you don't think about the formula. Just be like, oh, okay, intuitively, it makes sense that I'm just finding 39.9% of 567. How do I do that? I'm just going to multiply 0.399 times 567. Remember, like back in the beginning of the class, there was that random percent in decimal section. Like that's coming back. It's having its heyday here. Okay. And so we would say that, okay, so in this original survey, out of the 567 people surveyed, 226 would have said yes. They don't like uh, tattoos and body piercings, apparently, but whatever. Okay, and it says round to the nearest integer. So yeah, all right. So that was one. I have one last one I'm going to show you from 8.2, and then we'll wrap it up. I'm going to put timestamps on here so you guys can jump around if needed. Okay, and this last question here that I wanted to talk about from 8.2 was number 15. Okay, and this one's more heavy into the ideas area, not so much like I feel like the last ones we just did, the standard deviation, kind of get like, it's simplifying decimals. Ugh. And then we looked at how you would maybe need to solve for like the number of people, perhaps if they didn't tell us that, but they did tell us the proportion and the sample size. Okay, so lastly, this one says, the figure shows two sampling distributions for sample proportions when the population proportion is P equals 0.35, complete parts A and B. And then so they labeled these graphs. There's two, these like normal-ish looking curves, N equals 150 and N equals 3000. Okay, so just like before we even look at the questions, I just want to make sure this makes sense to us of what we're kind of looking at here. This is what we're talking about. We're going to build a sampling distribution. We're taking repeated samples of size 150 is the red curve, and then 3000 is the blue curve. So hopefully intuitively it makes sense that like if we take more samples, the larger the sample size, right, our graph is going to get closer together. Okay, for a couple different reasons. One is like the standard deviation formula, it divides by the square root of n, you know, but So anytime the n's getting bigger, like you're going to be dividing by a bigger number, but also hopefully kind of like intuitively it sort of makes sense, right? Is that the more samples you have, the more accurate you're going to be, right? The smaller the spread is going to be. Okay, but let's take a look what the questions are asking. It says, as the sample size increases, the mean of the sampling distribution stays the same. Yes, that is true. Okay, so they're just saying we don't even have to find anything here. This is just sort of like a theoretical big ideas question. Okay, so that's true. They're both still centered around that population proportion of 0.35 that they told us in directions, right? And then the next one says, as the sample size increases, explain how the standard deviation of the sampling distribution changes. Okay, so I kind of talked about this before we even looked at the question, but as the sample size gets bigger, the standard deviation is going to get smaller and the curve is going to be more narrow. And hopefully you can kind of see that with the graph too, right? So the red graph as n is 150, the blue graph as n is 3000. You can just kind of see that the blue graph is much taller, much more narrow, right? And it's because the standard deviation makes it kind of smushes it together a little bit more. So we're going to be looking for when n is larger, the standard deviation is smaller, so either B or C, and so the curve is narrow. That's whenever the standard deviation is smaller, the curve is always going to be more narrow. So I hope this was helpful. If you were struggling at all with either just kind of like the ideas in this section or calculating some of those decimals, and again, hopefully you can always send me Ask My Instructor questions, and I would be so happy to help answer them either just like with an email or a video. Okay, thanks class. Bye.